In this lesson, we are going to go through a comparison of series and parallel circuits using the examples on the screen here. And as you can see, the same components have been used in the series circuit as in the parallel circuit. So let's begin with identifying what those are. So there's the battery, then we have the resistor, and then we have this device here, which is called a diode. So a diode is a special type of device which only operates at a certain voltage. So it only works at a certain voltage. And then when it does work, the resistance drops to zero. So if you think of the formula V equals IR, for the voltage to go to infinity, the resistance basically goes close to zero, and then a certain current flows through it. So the best example of a diode would be like an LED, a light emitting diode. So on this side is the diode connected in the series circuit, and over here is in the parallel setup. Parallel circuits have branches. So what we're going to compare is the differences in current, voltage, and resistance across the two different setups. So let's begin with current. So the current is the flow of electrons, the flow of charge around the circuit. And for GCSE physics, grade 10 physics, we take current as flowing in the conventional direction, which is positive to negative. So from the positive terminal of the battery, which I've just marked out there in red, to the negative terminal. So it would be flowing this way as directed by the arrows I've just drawn in. So with current in a series circuit, the current is the same all the way around. And the reason why is because if you think of a series circuit as just one continuous loop, the electrons can only sort of go in one direction, would be a simplified way of looking at it. Whereas in a parallel circuit, you can see that there's branches. There's one and there's another one. When this happens, the current has, for want of a better term, a choice. And actually the current splits. So that's our first point, the current splits. And if you were going for, say, a run, and you was running along a concrete path and you came to a junction, and one fork of the junction is the concrete path continuing on, and then the other branch would be a sand route. So in other words, much harder to run along. So most people would opt for the concrete path, as it's easier to run along the concrete path than it is through sand. Well, it's the same idea with current. So when the current splits along these branches, so if we put some directional arrows in, you can have some going this way and then some going along that way. The current will take the path of least resistance. Most of the current will flow along the branch which has the lower resistance, and the remaining part will go along the branch which has the higher resistance. So in the case of this parallel setup, you can see that the diode is in series, if you like, with the 4 ohm resistor along that branch. So if I just underline this bit in red, and that branch will be of lower resistance because the diode has a resistance close to zero when it's in operation, which means the current has, the option of the 4 ohm path versus the 8 ohm path, and the 4 ohm path is going to be of lower resistance. So the takeaway there is current splits in parallel, but remains the same all the way around in series. The voltage is the energy per coulomb of charge, which means if you have a 3-volt battery, then it will supply 3 joules of energy per, certain quantity of charge. A coulomb of charge is a certain number of electrons. So just think of it as the energy supplied from the battery. That's the easiest way. So in this case, we can see we've got a 12-volt battery. So that'd be 12 joules of energy, electrical energy, supplied to the current. With voltage in series, it is shared. So voltage is shared amongst devices. So a device would be something like a bulb, a resistor, a fan, whatever's connected basically. But in parallel, the voltage is the same along each branch. So the voltage supplied along each branch will be, in this case, 12 volts. So 12 volt along that branch and 12 along that branch. So you can sort of see with these comparisons is with series and parallel, it's almost like literally opposite. So when it's one thing in series, it's almost the opposite in parallel. Right, finally is the idea of resistance I'd like to talk about. Resistance, the property of resistance is something that restricts the flow of charge. So something that slows charge down, if you like, and causes electrical energy to be manifested or turned into is heat energy. So just think of a light bulb, a traditional filament light bulb, where a current passes through a filament which is tightly coiled. It has a very high resistance, and that electrical energy is then expended as heat, which is so hot that it literally begins to glow and produces light. So resistance is something that restricts or slows down the flow of charge. So in series, the total resistance is very simple to work out. It's just the sum of the individual resistances. So if we say the total resistance is TR, then it'll be R1 plus R2 and so on. So this is obviously going to have a resistance. So that's R1, that's 4 ohms. And then R2 would be for this device. I know it's a diode, it would be close to 0, but pretend it was like a light bulb or something else. You just add up the individual resistances and that will give you a total resistance in series. But in parallel, that is not the case. In parallel, it's actually sort of fractional or reciprocal as it's known. So the total resistance in parallel is given by a different expression. It's 1 over TR is equal to 1 over R1 plus 1 over R2. So it's reciprocal, which means it's expressed as a fraction. So as you can see from the equation, 1 over TR is equal to 1 over R1. So again, that will be R1. And let's call that one R2. You can just see from the mathematics of it, when you add those resistances together and work out TR, the total resistance in parallel will therefore always be less than the resistance in series. Just mathematically, you can see that. Just to prove a point, let's just say that was 2 ohms and that was 5 ohms. Well, my total resistance would be 7 ohms. Whereas if I go ahead and work that out in a parallel setup, 1 over TR equals, it'll be 1 over 2 plus 1 over 5. And I don't really need to go any further to show that when you add a half to a fifth, it is not going to be 7 ohms. It will be a lot less. So the takeaway from this is that, and this is the main point here, resistance in parallel is less than series. So just to recap, in series circuits, the current is the same all the way around, but in parallel circuits, it splits, and the majority of the current goes along the path of least resistance. With series circuits, the voltage is shared amongst the different devices or components, whatever you want to call them. Whereas in a parallel setup, the voltage is the same along each branch. And then finally, the resistance in series is the sum of the individual resistances, whereas in parallel, it is reciprocal, which means it's 1 over the total resistance is equal to 1 over the other resistances added up. Now that we have this knowledge and this understanding of the principal differences between series and parallel, the next thing to do is to put that into action with some calculations for series and parallel circuits using V equals IR, P equals IV, Q equals IT. So there are some of the 3 popular formulas you see with these electricity questions. So voltage equals current times resistance for the first one. Power equals current times voltage for the second one. And then charge is equal to current times time. So if you'd like to see how we work out calculations for series and parallel circuits and how this is all brought together, please check out the videos in the link in the description below. And do like and subscribe. Thanks for watching.